Uh, Good evening, everyone. Thanks you for coming to this talk. As it was mentioned, we will be talking about using GraphQL as an umbrella for microservices. So let me briefly introduce myself. My name is Artur, and I'm a back engineer in the company called Mirumee Software, where we create various solutions for our customers, mostly e-commerce platforms, sometimes more complex ones that are using microservices. And why GraphQL? So let me briefly ask you first a question. How we are dealing with the microservice at first. Let's do a quick exercise at first. Did you ever use microservices on your own in your project? Please raise your hand. All right, near the full house. However, please raise your hand if you always did that by the book. So all those services were loosely coupled with each other. So and you have always clear boundaries between responsibilities of each service. Please raise your hand. Well, near zero, myself included, right? So that quick example shows us that microservices as a pattern is a complex architecture. And as developers, we are always dealing with various trade-offs, right? So the devs would like to have clear, modern infrastructure. However, the business would like to have more features. And always you need to do some trade-offs at some point. And the more you do those trade-offs, the more tech debt you are accumulating. Because sometimes you just need to sacrifice the technical excellence for the closest deadline, right? And at some point, instead of having clearly separated, shiny microservice architecture, you are ending in a situation like that. So everything ends up interconnected with each other, everything knows about itself, and it's just a mess, or maybe a distributed monolith type of architecture. And well, I know that because I've been there a few times. And the purpose of this talk is to show you how I try to escape from that kind of mess. So all the examples that I will show you were part of a real system that we were operating. So what was the initial state? The project itself was, at the first glance, quite simple e-commerce platform, because we are just taking orders from the customers, processing them, using some external APIs, and just shipping them further, right? And at the beginning, we were operating roughly about 15-something microservices that were in a different shapes. So the more modern ones were using cool tech like FastAPI. Some others, older ones, were using Django or even Tornado at some point, right? So the architecture was different between those services. So what were the components of the system? We had an auth service because we needed to somehow know who our users are. Later on, we had orders service that kept history of all the orders that were placed in the system. And finally, we had products service that was informing us what are we going to sell. Of course, there were other components, but they are less important in that case. All those services have one factor in common. They were exposing REST API. And sometimes, as I mentioned before, that REST API was also used internally. So services could call each other internally as well. Sometimes they were also communicating using asynchronous events exchanged with RabbitMQ queues. So that's slightly a better approach, in my opinion. But up to this point, that architecture doesn't look that bad, right? So what's on the front end? On the front end, we have React-based applications. So for example, a storefront application where the customers are essentially buying stuff from us, right? And once customer did a purchase, we need oversee that purchase. We need our employees to take a look on all the orders, do some reporting, and in general, manage the platform. So up to this point, we had just 2 applications, right? So our front engineers were trying to keep them as simple as possible, and it worked quite well in their case. However, on the other hand, the backend engineers wanted to reduce that tech debt because they needed to reduce the number of services in general. But from the business, there is a new requirement that we need that new and shiny experience for new checkout application. And it's completely different beast from what we had before. So essentially, we need to spin off a new application. And also, there are some rumors about having a mobile app, because why not? So up to this point, how those systems are communicating. So as I mentioned, the storefront is a primary point of contact between our customers and our system. So storefront does auth because it has to authenticate users somehow. Also, it needs to display the information about the past orders of the customer. And finally, we would need that customer to buy stuff. So we need to display products. And for sure, you see when I'm coming to. So all those services at some point in time were knowing exactly about how that API is structured and where to find that information that they are looking for. And it was quite a bad situation because the front engineers wanted to just live in peace and don't need to refactor stuff. But the backend engineers, on the other hand, wanted to refactor stuff, and they want to reduce number of services, maybe change how the data is kept in the database, maybe create some new services and move stuff around. So we started to think how to untangle that problem. So the first approach and first idea that we tried was to introduce backend for frontend. It's a clear pattern to separate the application logic dedicated for each API consumer, right? So storefront could receive its own abstraction on top of the core services, right? Back office API also could do the same thing, and so on. It was quite promising. However, it was not even remotely close to reducing number of services because it will just create more of them, however, in a slightly more organized manner. So what to do next? We were quite happy with that concept of abstracting the core services and creating that dedicated API gateway layer. So we thought, well, maybe just create one API gateway. So what are the downsides of that approach? Of course, it could become at some point in time a single point of failure. However, we thought that it would be a good enough approach because we just have, containers and all that stuff, so we can scale up. So that API gateway will be always up. However, how to use an API gateway in order to serve that data for all of those different those different consumers. And here GraphQL comes into play. So what is GraphQL? GraphQL is primary query language that was initially developed at Facebook, however currently is open sourced. And the quite good benefit of the GraphQL as a language is that it's static typed, so it could act as a contract between your backend API and your frontend consumers. And also it's protocol agnostic, so it's not deeply tied into HTTP. You can just format GraphQL, format your message in GraphQL and just send it over any medium you want. So how it looks? In GraphQL, you define something that is called GraphQL schema, which could be referenced as essentially type system for your API. So you statically define what kind of data you will be serving. So in that case, we have query that will return orders, And it will return always an array of stuff that is type of order, because the exclamation mark means that the value will never become null. So that's quite handy. However, how it's useful for the clients, how it works, and why it's good. So GraphQL server and client will be using similar set of APIs, similar set of tools. The client will most likely use TypeScript or some tooling to deal with GraphQL. So GraphQL server exposes schema, that schema document that we just seen. And client at first fetches that schema because it will do validation of those queries and mutations that it will try to make against our server. So we achieve multiple layers of validation here, because the client would never receive, would never return a query that it just doesn't match the schema. Once the data that client would like to send matches the schema, it will execute the queries and mutations against the server. And what's cool, GraphQL server calculates the response, and it will respond to the client with the data that it was requested for. So the important piece is here that the server will never return more data than it was requested. So that's how the client could shape the size of data that it will need to display. Because, for example, when we are the mobile application consumer, we don't need potentially a full set of order data features, right? And also that the GraphQL schema has a few other benefits. It could act as your live documentation of your API, because you for sure are creating that structure statically, right? And you have that nice typing system. However, also you gain things like those schema directives, like @deprecated. You can deprecate fields and operations on the schema level, and when you do that, your API consumers will just receive a highlight that certain field or operation is no longer available. However, so it will be still available, right? Because it's in the schema, but you shouldn't use that anymore. And also that help text will be provided within the schema definition. So since we are on the Python conference, how to use GraphQL in Python? As with everything, there are several approaches to do that. The oldest one and the most mature one is the Graph in Python library, and it presents something that is called the code-first approach. So it means that you at first write Python code in classes that for me look quite similar to how Django REST framework serializers do work. So essentially you're creating your schema with the framework provided abstractions, and the schema gets created in flight. The second library that does similar thing is Strawberry. Strawberry is a bit more modern because it uses Python type annotations in order to create those types for GraphQL. However, it's still the code-first approach. So you need to write code in Python in order to receive the schema. So the question is, could that be done different? Well, yes, it could be done different. You can first create the schema and then create your code. So here the Ariadne library comes into play. It presents the schema-first approach, where you need to write schemas in the .graphql files in the format that I have presented before. Later on, you are importing the schema into your code base, and then you are wiring your resolvers into certain schema operations. So the most important question is, which one should you use? And as everything in IT, it depends. It strongly depends on your use case. And let's quickly compare those two approaches. So within Schema first, your front-end engineers could easily collaborate and contribute into your API, because essentially they could request an API that behaves in a certain way because they know what kind of information they want to display, right? And that was a very strong deal breaker for us where we choose that particular approach, because our front-end team would like to contribute and share their feedback on the schema, but they didn't do Python. They did JavaScript. However, on the code first, it's heavily backend focused. So when you are the team of backend developers and you don't need to collaborate closely with the front-end guys and you are just exposing an API, code first approach could be fine. However, you should be aware that it's harder to predict what kind of schema will be generated, because all of that schema is created by the framework abstractions. So if the framework has a bug or doesn't support certain type of operation, it will be quite hard to determine what is in the output. Within the schema first, you receive a full control over the schema, because the schema is essentially another file in your code repository, right? So it's easy to track the changes and show and see full diff on the pull request. However, it could be also a downside, because you have more code to maintain, right? All right, so we have selected an approach. So how GraphQL features could be useful when we are dealing with an API gateway. Let's recall the graph of the infrastructure that we are operating and our schema. So in that example, we will be displaying a list of orders placed by a given user by providing the user's ID. Each order has order lines, so the list of items that were ordered, and that kind of information will originate from the order service, because it's the single source of truth of what kind of stuff we have been ordered. However, the business would like to have a reorder feature. So, for example, if I ordered a coffee, I would like to offer another order for that coffee. However, the order service doesn't know if that product is on stock and what its current price, because it could have changed over time. So that piece of information will be extracted from the product service, and the combined information will be returned to the storefront. So how it's done under the hood? Under the hood, there is an asynchronous field resolution. So when you send that GraphQL formatted query for your backend, it will match the resolvers, so the Python functions, from your query, and it will be asynchronously, it will execute them asynchronously. And what's cool about that is that you can do whatever you want here. You could do that database lookup directly, HTTP call, cache call, search call, whatever. And also, if you are dealing with some kind of legacy system, you can rearrange the data and shape it in a way that it's more useful for your front ends. So that's quite cool, right? So maybe let's talk about some drawbacks and caveats that you need to be aware before you go that path. First of all, error handling. Error handling in GraphQL, it's not even close to the thing that you are familiar with when you are using REST API, right? It's a lot more verbose, and it's quite hard to read sometimes. And moreover, when the query is valid in terms of syntax, it will be returned from the HTTP server as 200 OK, because essentially it succeeded, right? The data could be partially scattered, but the query itself succeeded. So it's onto your client, the front-end client, the API consumer, to deal with that problem. and maybe display some error message that part of your data is not available. And that's main reason why it's not perfectly suited for machine-to-machine communication because of its verbosity. In our scenario, we kept the REST APIs of the microservices because it was just more useful for debugging, automated tests, and so on. And we just translate the REST calls to GraphQL on the API gateway layer. And also, we have more tools to deal with REST on the backend. The other problem are file uploads. GraphQL's schema definition language doesn't support types of binary data. Of course, you can hack it around and just smash base64 encoded string into the query, but it could become a performance problem, and I know that. It was a painful lesson. So it's better to use a direct cloud upload into your storage because your client doesn't essentially need to transfer all that data through your API. It will be faster using cloud upload. And other problem could be referenced with naming because as you've seen on that first example, everything is like in a single namespace by default, right? So when we create our API starting from the orders, so what the order is the order a thing that is seen by the admin, or is the order that is seen by the end customer? That's tricky because with a single namespace, you need to be very careful how to pick your names. I really recommend that article because it shows you the way how to avoid that kind of problem. And the final one, and I believe it's the most difficult one, is the N+1 queries. So when you already coded your way, coded your API gateway in a way that I presented. So your orders by user query will call order service, and for each of the order lines, it will expand the stock level and the price. It will scale well for single line item orders, but what about orders when the customer ordered 100 of different products? So of course, by default, it will hammer the products API 100 times for each individual line item. And how to solve that problem? Thanks to the asynchronous field resolution that I mentioned before, you could use the quite fancy pattern that is called the data loader. And the data loader will allow you to group your calls. So it will see that you are trying to load in a single query resolution, you're trying to load products over and over again. And instead of doing 100 calls for a single product, you could do one call for 100 of products to gain more performance here. So wrapping up, if you are operating a microservice-oriented system and you don't have an API gateway, I really recommend having one because it allows you to add some of the logic on top of your services and maybe do some magic with the data. If you enjoyed what you have seen here, consider using GraphQL. It's quite a powerful tool. However, it's not a silver bullet for every problems that you could have during that journey. Thanks a lot. Do you have any questions?
Congrats for your talk, very beautiful one. GraphQL is required to be used with some specific type of database, or this would be one extreme. The other extreme would say, is GraphQL database agnostic too, besides protocol agnostic? In which part of this spectrum GraphQL is?
So GraphQL is is not tied to any database. It's a syntax how to format your messages between your API consumer and your backend application. So you could use whatever you want as a backend, as your database. It could be file, database with Postgres, or whatever instance you would like to have. It's not specific to a single database.
Okay, thank you very much.
Hi, thank you for the talk. I was wondering the schema first approach. How is the workflow? How do you keep the schema and the Python code in sync? Is there any automation there?
That's a good question. So in our scenario, we keep the schema code in the same code repository as the resolver's code, and it works quite well because it lets you to just keep the things close to each other. We tried to use a separate pattern to keep the schema in a completely different repo, but it's a lot of hassle to keep everything up to date. So the best way to do that is just to use the single service repository for that. And for the automation, well, we didn't decide to do any automation there because of the code first approach. So it's required to write the schema by hand, but it also gives you an opportunity to, for example, execute some CI/CD tooling to see if you, for example, introduce backwards incompatible changes and that kind of stuff.
Wait.
Quick question. In JavaScript, they have the Apollo server.
Yes.
Do we have something like that in Python?
The Apollo server toolkit is quite vast. They offer you, the type generators and that kind of stuff. I recommend you to take a look on the Ariadne CodeGen project. This is an attempt of doing something similar. So, for example, if you have your schema and you define your GraphQL query, it could generate Python code for you to reduce the size of the boilerplate. I'm not aware of any similar attempts of reproducing the Apollo system, unfortunately, in Python.
Great presentation. How you are resolving monitoring and what you use for monitoring the GraphQL queries and so on?
Yeah, that's a good one because you cannot use the standard approach because everything is the single endpoint. You could instrument your resolvers with for example, OpenTelemetry, and you could do that on per resolver basis. Or you could inject some sort of a middleware during in the code of the IPA gateway itself to see what kind of operations are taking the most time. And that's the approach that we are using.
Okay, thank you.
What are some of the testing strategies you have for this?
First of all, when we are using GraphQL in order to perform certain REST calls, we are using snapshot testing on the API gateway layer. So we are mocking up the REST responses. And another layer of testing is the integration testing of the entire thing. So once things are deployed to the integrations environment, we just do end-to-end tests with everything.
So are you using like Playwright or Cypress? Or
yes,
something?
for the end-to-end tests, yes. For the snapshot testing, we are using the lib that is called ZeroPy. That's a plugin to PyTest.
Cool, great talk.
Thank you for your talk. I have a question, and what strategy in like a version compatibility did you choose? So if we expose some new field on our backends, and you need to push it to parsers gateway, so how it happened?
Yes, that's a slightly negative point because sometimes you need to do your API like twice. First, expose the internal facing API, and later on expose the public facing API. So the strategy depends in general on how do you introduce that feature, because sometimes the certain type of the client-facing application could use several features from the backend. So we are sometimes exposing the final type on the GraphQL later on. But the cool thing about the schema-first approach is that you can establish the schema first, and when you have the schema, the front-end developers could easily mock it up, and they don't need the real backend because they will know the structure. The structure always acts as a contract between your backend and your frontend.
Any other questions? Probably I have one, like clarification more about the monitoring thing. So when you said about the API gateway itself, and I'm curious because I'm kind of maintaining the gateways in the company where I'm working now, it's like some kind of service that you have, right? That's what you call API gateway. That actually implements the schema understanding and after like calling the underlying services.
Yes, exactly. This is implemented as just starlet web application, which has mounted that GraphQL thing into it. So essentially the API gateway is just another Python web service.
Okay, so it just behave like a reverse process or something
Yes.
like that. Okay.
Yes, you can do whatever you want there. You plug in OpenTelemetry, Sentry, like in a just normal API.
Okay. No, more like a curious in terms of like so-called upstream or backend services. The monitoring is supposed to be relatively easy. There shouldn't be any kind of problems. Right. If there are any other questions, no? Last second. All right. Thank you very much.
Thank you.